In this video, we will try to learn about some basics of electrons magnetic moment. So, and in studying the electrons magnetic moment, we will have idea about Bohr magneton, gyrometric ratio, etc. So, in this process, we will come to know those physical parameters. Yes, I think everything is visible. So as you know, that if I define an electron like that it is, suppose here it is electron and it is moving around some nucleus, and it is the radial distance from the nucleus, and suppose think about that the electron is moving around this uh, nucleus with a velocity of v, suppose. Okay. And obviously, if electron moves around some line, or in precisely through a line conductor, so we will get a current just opposite to that direction, right? Because electron is negative charge, so we have to define current in the opposite direction. So for this move, rotation of electron, you will get some, suppose, magnetic moment. Suppose I am defining it as mu, right? So it have to be perpendicular to the this plane, this circular plane. Fine. So as you know, it is known to you that we define the magnetic moment for a charged particle in this way. Suppose I and D is the cross section area of this circular region. Okay, you know it. I think already you have read all those things in your classic, electrodynamics part, electromagnetism part. So fine. So now, if I try to find out what is I actually in this picture, or where we have in the system. Uh, so how can we define uh, current? So it is, you can understand that charge suppose here, so v is the velocity per unit time, so we need not to bother about the time actually. Okay, so I will write the expression, you will understand. Suppose that's right, ev, this is something in charge. Now suppose 2 pi r, this is perimeter. So this defines the actually current, dq by dt, per unit charge by per unit time, the flow of per unit charge by unit time. So if he gives the total charge in this line by unit time, and if I divide by 2 pi r, you will get current. Fine. So this is fine. Now, if if I put this expression there, so you will get so you will get one thing you have to understand here. Since the current is in the opposite direction of the movement of electron, so we can bring a negative sign. So, or you can put a charge there, a charge of electron. It is denoted by negative sign. So fine. If I put this I and dA as pi r square, it is very simple formula. So putting all those things, you will get this like equation. Okay. Mm, so, okay. So this is a very simplified. Let me write in a simple way. E V okay, 2 pi okay R 2. So I think video is not too clear. Still okay. Okay. So now you know that angular momentum we defined as across v r cross v, since we are just concentrating on the magnitude, so we can write to m. You know na, mvr is angular momentum, so just I have replaced. So finally, if I write in a vector form, it is a vector actually. So I can e by 2m, which is a constant part, and l. Right. So here I think the picture sounds like that. This angular momentum actually just in the opposite direction of the electron's magnetic moment. This is all we are talking about, only the orbital things. Okay, uh, just orbital things. So fine. Now, as you know from the Bohr quantization rule, that already you have read those things from your class, I mean 7 or 8 physics. So 7 or 8 class. So uh, you know that in every I mean orbital has a integer value of angular moment. So if that is true, so we have to redefine these things in a different way. You can see here. So for the time being, I am giving a subscript there. Okay. So mu l. Now I can write in this way. Okay. By h card. So this is because of just because of the Bohr quantization rule. Because you know that this L will keep some integer value of h card. Already it is I mean given by Bohr theory. So if it is true, so this is actually the I mean, unitless, dimensionless figure. So this mu b will give the dimension of the magnetic moment. So this mu b, is like that. Mu b is EH cut by 2m. Okay, just we have redefined this expression in this way, nothing else. So this thing is called Bohr magneton. This thing is called Bohr magneton. So you can see that all the terms in Bohr magneton are constant. So if you put all the values, you will get almost something like it is the standard value actually. 0.1 10 to the power minus 24. Now unit is hmm, fine. So this magnetic moment, electron magnetic moment, actually is written in more generalized form. What is the so after this discussion we will do a discussion about the Stern-Gerlach experiment. There you will understand why we are giving a generalized form of this magnetic moment. Now we will talk about the total angular momentum. So later we will clear this term, why it is total and why this n is just actually orbital angular momentum. So if J is the total angular momentum, so A, so mu J I can define it. So this is defined as just we are writing this term from this form actually. It's this like now you can see that here we have introduced new term written as G. So for this part, electron's magnetic moment actually G has been considered as 1. So for that you cannot. So G is actually dimensionless constant. You can understand that mu b is has a unit of mu j, so G has to be dimensionless. So this is called actually gyromagnetic ratio. Fine. This is okay. Now we'll talk about some interaction with the magnetic field. This is actually required for our just the next part, that is the description of Stern-Gerlach experiment. So let me discuss about this interaction with magnetic field. Fine. Actually, what we will talk about now is actually known to you. You will, if you look at the expression, you will understand that already we have read all those things. So, if I say that an atom is placed in a magnetic field B, so an atom with magnetic moment mu is placed in a magnetic field B. So the energy of interaction, potential energy, that is potential energy, we know is written as minus mu dot B, right? So what I told that atom has magnetic moment mu and placed in a magnetic field of V. So we will get interaction energy as minus mu V dot B. Fine. So at the same time, that atom will feel a torque. So actually, people defines it as gamma. So this is defined as mu cross B. You know it, right? Uh, and force experienced by the atom is looks somewhat like this. Minus grad of that energy. Fine. So as you can understand, if x is can be written mu dot del b del x. Similarly, if y is mu dot del b del y. Similarly, if z. Okay, let me write this del b del z. Fine. So now here one more physical parameter come into action, that is called the Larmor angular frequency. So what is that? So if we put an atom or charged particle in a homogeneous magnetic field, or here just the charged particle rotating, I mean moving charged particle with magnetic moment mu, if we place it in a homogeneous magnetic field, so what will happen actually? I mean this magnetic moment will precede with a frequency, particular constant frequency will precede with a constant frequency, and that frequency is called actually Larmor. So that is defined as Larmor frequency, that is called. So mu b h cut b, like that. So this is actually called Larmor Larmor frequency. So this is called Larmor frequency. Now, what will happen if we place the same charged particle in inhomogeneous magnetic field? So that will feel a force. That will feel a force. You can understand. Huh? So if and only we place a charged particle in a non-uniform magnetic field, they, they will feel a force, and this thing will be actually has been used in the Stern-Gerlach experiment. That is the main you can say requirement of their experiment. Okay,